Hi, AP Calculus students. I had to bust my 3.4 workout video into two pieces. So there's two of them. This is going to be 19, 24, and 88. Let's actually start over here with 19 and 24. They are both in the same section, and the book is asking for where these functions are concave up, concave down, or where they have inflection points. So both of them are polynomials, so their domains are from negative infinity to infinity. And so just ignore number 24 first, right? We're just working on number 19. We're going to do that second derivative chart. So let's see. So the first derivative is I'm going to bring the 4 out front and multiply it by 1/2. That's 2x cubed. Plus, I'm going to bring the 3, 6x squared. There's the first derivative. The second derivative would be 6x squared plus 12x. Yes, okay. Where are the critical points? Let's see, critical points. Undefined, whoops, critical point on the inside. Critical point, undefined, defined everywhere. It's a quadratic. Where is this equal to 0? I think I need to factor it to see. Let's see, 0 equals 6x. And when I factor it, that leaves an x plus 2. Let me set 6x squared plus, yep, that looks good. So that happens at x equals 0 and x equals 2. So those are the critical points that are going to split up our intervals. Let's go ahead and do that. Just giving myself some room. Boy, do I need new markers. Let me see if I can pick up a different one and see if it's a little better. There we go. Intervals, negative infinity. Oh, that's better. 2, 0. 0 to 2. 2 to infinity. All right. Let's take a look. Test values. Negative 1, 1, and 3. Concavity. Let's see, when we put, we're using the second derivative. When I put a negative 1 in here, I'm going to get a negative out. When I put a 1 in, positive. And when I put a 3 in, right, let's see, they're both positive. Let's take a look here. So inflection, oh, I guess I have to say what the concavity is, don't I? So that would be concave down, concave up, concave up. That feels weird, right? We're used to it switching back and forth, but it does in fact happen. Where are my IPs? Let's see, that's where the concavity changes. So that would be at 0, because it goes concave down to concave up. That would happen at 0. And let's see, when I put that 0 in, I get a 0 out. So that would happen at 0, 0. No IP right here, where 2, because the concavity does not change sign. Let's actually look at it on the calculator. Let's see, zoom 6. There we go. It went a little off the screen, but you can see there is, in fact, an inflection point at 0, 0, right? And that it does change concavity there, and that there's no other inflection points. I don't see the concavity changing. There we go. All right, let's try number 24. We are doing the same thing with 24. So we'll get rid of 19. There we go. All right, let's take a look here. Okay, let's see, first derivative, that would be 8x cubed minus 8. I keep checking because I'm tired, so I want to make sure I didn't do it wrong. 8x cubed minus 8. The second derivative is 24x squared. Right, bring that 3 out front, multiply it, reduce it by 1. Our critical points, undefined. This is a quadratic that is defined everywhere. Where is this equal to 0? At 0. Let's do our chart. Intervals, negative infinity to 0, 0 to infinity. Test values, negative 1 and 1. Concavity, up or down. When we put in it, they're both going to be positive, right? Because we're only going to get a positive out here no matter what we put in for x. Positive and positive. So this function is concave up everywhere. And it has no IP because there was no concavity change. You know what? Let's put that in. Right? We did for the last one. Let's take a look. 2x to the 4th. Because, right, we're used to seeing concavity changes. They do that a lot because they want you to be able to see them, right? Zoom 6. Apparently, this is concave up everywhere. Let's take a look. And it certainly is. That is concave up everywhere. So we're right. Let's do problem number 88. So show that the inflection point of the function that I wrote lies midway between its extrema. Now, extrema are max and mins. So I think I have to do a first derivative chart and a second derivative chart, right? Let's take a look at that. Okay, right, max and mins here. Okay, so let's work on the first derivative. I'll do that underneath and we'll do the second derivative to the right. Okay, first of all, discontinuities, none. Right, because this is a quadratic that's linear, they're being multiplied, it's actually cubic. So negative infinity to infinity for both of our first and second derivative charts, right? We could actually combine derivative charts. That's what we do in 3-6, but I'll do them separate here since you haven't learned that yet. All right, let's find that first derivative. I'm going to use the product rule and I'll need a chain rule here. The derivative of x is 1 times x minus 6 squared, plus I'm going to keep my x and multiply by the derivative of x minus 6 squared. So anything squared is 2 times anything to the first. And then the derivative of the inside function is a 1 by the chain rule, but I checked, right? So I won't write the 1. So let's just clean that up a little bit. I think I actually want to take a look here. I can factor in a base of x minus 6 out of both, right? There's 1 here and 2 here, right? So when I factor that out, this one's gone and that one has 1 left. So if you notice, I have x plus 2x is 3x minus 6, right? Critical points, undefined, polynomial defined everywhere. Where is this equal to 0? It's really easy to see now because it's factored. So that happens at 2 and 6. All right, let's make our chart. First derivative chart. Here we go. Intervals, negative infinity to 2, 2 to 6, 6 to infinity. Make sure I'm still on the screen. I am. Okay. Test values, 0, 4, and 7. First derivative. When I put a 0, I'm looking here. The factored form is the easiest, right? Because I can tell if it's positive or negative. A 0 here and here is a negative times a negative is a positive. A 4 here is a negative times a positive. A 7 makes them both positive. There we go. So this is a max located at 2, right? And when I put the 2 in, let's see, 2 minus 6, negative 4 squared is a 16 times 2 is 32, right? Because it went up and down, right? And then a minimum. The minimum happens at 4, right? Because it goes, yep, the minimum happens, oh, I'm wrong, 6. There we go. That's a 6 right there. When I put a 6 into the function, oh, I get a 0 out. Here we go. Okay, max at an x of 2, minimum at an x of 6. Let's do the second derivative, find out where that IP is. And apparently it's right in between an x of 2 and an x of 6, which would make an x of 4. So I'm hoping that's what I get. Okay, so the second derivative would be, I'm going to use the product rule here. The derivative of x minus 6 is 1 times 3x minus 6. Plus, I'm going to keep my x minus 6 and multiply it by the derivative of 3x minus 6, which is 3. Let's just clean that up a little bit. Let's see, I have a 3x and a 3x, so that's 6x, and I have a minus 6 and a minus 18, so a minus 24. Awesome. Where are those critical points? Undefined. It's linear, defined everywhere. Where is this equal to 0? Oh, at x equals 4. Awesome. You almost feel like you could stop now, but we do, that's just a critical point. We do have to prove it's an inflection point, that the concavity changes. So from negative infinity to 4, and then from 4 to infinity. There we go. Test values. 0, 5. Concavity. When I put a 4 in, let's see, when I put a 0 in, you can really tell I'm tired. I'm just saying anything. Now I'm just saying any number that comes into my head. Sorry, thanks for laughing with me. When I put a 0 in, I get a negative. When I put a 5 in, I get a positive. There is obviously an IP at x equals 4. I could go ahead and get the y, but 4, an x of 4 is midway in between an x of 2 and an x of 6, so I'm good. So I'm done. It must be time for a nap for me. Have a good day.